first question. Looks like we are finding first and second derivatives. We're looking at intervals of increase. Okay, we should be able to do this relatively straightforwardly using our rules. So x cubed, 3x squared. We have 3x squared, that's going to go to 6x. And then we have a line of slope negative 240, so we'll take the negative 240. For the second derivative, we will just repeat that process. So 3 times 2 is 6. And then our last two terms here, again, are a line. And this time we have a slope of 6. So here's our first and second derivatives. With these, hopefully we can figure out intervals of increase and decrease, including the endpoints in the interval. So intervals, I'm trying to remember, it's been a while. Intervals of increase are when the first derivative is positive. Is that how this works? Usually when I teach this section of the course, I'm usually just like, you make a first derivative chart, make a second derivative chart, or one or the other, and just kind of figure out what's going on. Let's take our first derivative. Let's see what the first derivative is going to give us with regards to some information. So let's figure out where our maxes and mins are going to be. That's probably going to be helpful. Oh, here we go.
Time for a pop quiz.
Let's see. Let's go into equation mode. Let's solve a quadratic equation. Let's throw in 3 and 6 and negative 240. We get x is equal to 8 and x is equal to negative 10. So these are the positions basically along the x-axis. These are our values where we could have a max or a min. And typically doing a first derivative chart would give us some indication about whether or not they're maxes or mins. So what I might do from here if I'm trying to find intervals or trying to classify these two particular x values is I might kind of take my number line and I might plot these 2 points. And then I want to think about choosing test values. And this is a polynomial, so we don't have any like asymptotes or asymptotic behavior that we have to worry about. So I should theoretically just be able to pick x values inside these intervals. So we have an interval that's in between, for example, negative 10 to positive 8. So I could take x is equal to 0 here as my test point. Like I'm just picking some x value inside the intervals. I need something that's bigger than 8, so 9 or 10. 10 is usually easy to work with. And then I need something a little bit less than negative 10, so maybe we'll take negative 11. Right? It doesn't really matter what values I pick as long as they're in the section of the number line that I want to work with. Now, what we're going to be doing is we're going to be evaluating f at the particular at the particular value, and then getting a sense of what's happening. So if I sub 0 in, so if I take 0 and I sub 0 into my first derivative, I'm going to get, and I should be a little bit careful here, I'm subbing it in here. So if I sub 0 in up here, I should get negative 240. And then we'll just kind of repeat this process with our other two test points as well to get an idea of what the signs look like for my first derivative. So if I put 10 in, what do we get? 300 plus 60. So 360 take 240. 360 take 240. What is it, like 120? So here we'll get 120. And then the last thing we'll need to do is we'll need to plug negative 11 into that first derivative as well. So we'll do 3 times negative 11 squared plus 6 times negative 11 minus 240. And we get 57. Now, the particular numbers aren't important. It's actually the signs of the numbers that are important. So let's take a look at the signs. And so the idea is the signs are going to start to give us some indication about what this function looks like. So I know at 8 and negative 10, I have horizontal tangent lines. That's what this equation gave me up here. I got a slope of 0 at these particular x values. And then I have kind of positive slopes before negative 10, negative slopes between, and then positive slopes after. Let's take a quick break to listen to the song. Back to the question. I think that once we have a general idea of what our function looks like, then we can start to say things like we're increasing over here, we're increasing over here, and we're decreasing in the middle. At least that's the general movement of the derivatives or the slopes of these tangent lines. So if we come back up here, we need intervals of increase. So that's going to be from minus infinity. They say to include the endpoint, so to negative 10. And then we're going to union 8 to positive infinity. That should take the do the trick for our increasing areas. And then we have this one region in the middle where we're decreasing. That's going to be for all values in between negative 10 to positive 8. Now, I probably don't really have to do much work here. I think the first derivative test also gives me a good indication about where things are concave up and down. So it looks like we're concave down. Actually, you know what? I might need to find that singular point somewhere here in the middle, don't I? I need to find that inflection point. Oh. No Reese on the couch today. Sorry, Anders. So why don't we grab the second derivative, find that inflection point. So we need 6x plus 6 is equal to 0. So that gives me 6x is equal to minus 6, or x is equal to negative 1. So at negative 1, we should have our what we call our inflection point. So all of the values to the left of negative 1, we're going to be in a region over there like that's concave down. So everything's kind of facing downwards. If it were to rain above this, all the water would leak off. And on the right-hand side of negative 1, we're concave up, so if it was raining, it would kind of gather water into a puddle, is kind of how I always think about concavity with regards to these two-dimensional graphs. So downwards concavity looks like it's happening from minus infinity up to minus 1. It says to include the endpoint, so I will. And then we're concave up negative 1 to positive infinity. So that's how we utilize our first and second derivatives to get a little bit of that work done for us. Can we do this one? This 7's kind of awkward, I'm not going to lie. But we should be able to reasonably do this. I'm just going to think about this as maybe x to the 4 over 7 minus 32x squared over 7. It's going to be a bit weird with these 7's, but I suppose it just follows the usual derivative rule. So we're going to get 4x cubed over 7 minus 64 x over 7. And then if I want to find the second derivative, I just repeat that process. 4 times 3 is 12x squared over 7 minus 64 over 7. Now the weird part here is probably going to be trying to find our intervals. I feel like doing the intervals with the 7 is going to be a little bit awkward. So maybe let's start by trying to get a rough idea of what this picture looks like using the first derivative. And what we want to do here, I think, is just set this first derivative equal to 0. We're going to find all the potential spots where we could have a critical value. Oh, I see. So they've probably given us one here where we're going to have a inflection point instead, right? So we can multiply everything by 7. That gives us 4x cubed take away 64x is equal to 0. And then let's factor out 4x. So that'll give us x squared minus 16. So that's going to give us 3 potential places for critical points. So there's a potential for a critical point at 0, and then a potential at both plus and minus 4 as well. The only way that we're really going to have an idea about kind of roughly what this function looks like is by doing this number line diagram like we did the last time. So here we're going to need x is equal to 0. We're going to need positive 4 and negative 4. And we'll just try to find some values inside these intervals that seem reasonable to sub into the first derivative. So I could take maybe negative 1 and positive 1. Those seem good. And then we can take maybe 5 and negative 5. And remember, I don't really care about the value of the first derivative that much. I care more so about what the sign of the first derivative is. So maybe let me just plug this in. So let's see, we need 4 times something over 7. And this thing needs to be cubed. And then we need 64 times that something over 7. So let's pop back over here. Let's just start with our negative 5. So negative 5 is one of the test values that we thought might be helpful. So putting that one in, I get negative. Well, I don't really care, like I said, about the number, but I got negative 180 over 7. I really just care about the sign. That's what I want. So I want the sign of f prime. So we have a negative sign here. How does that change if I plug in something in the next interval? So something like negative 1. It gives me a positive sign now, so positive 60 over 7. I suspect that if we do positive 1, we get the same thing, right? No, we get a negative. Okay, so a negative sign here. I guess this is an odd function then, so I should suspect this last one hopefully to be positive if everything goes well. So we have a 5, and we have 5, and that does give me indeed a positive sign on that first derivative. So now I have a rough idea about what our original function looks like. We're going to have something like this. We have, I guess, a 0 here, and then a positive, and then a 0 here, and then a negative, and then a 0 here, and then a positive. So we're going to get this W kind of shape happening with our original function based on the analysis of our first derivative. Now, if we could, so I kind of can see that there's like concavity up here and concavity up here and concavity down here. I can kind of see that behavior, but getting an idea of like exactly where these inflection points happen would be super helpful. And the only way to do that is to do just a quick f double prime analysis.
Zeta boring. Just tell me the problem, and I'll show you how a genius like me solves it. Don't keep me waiting.
I think that's our second derivative. It's minus 64, right? Minus 64 over 7. So let's grab our second derivative. Let's set that equal to 0. Let's go ahead and try to solve for x. So we have 12x squared. Take 64 is equal to 0. Can we do some divisions? We can divide by 4. 64, does 64 have a factor of 3 in it? I don't think so. No, I think 64 just has 2's. So that means 3x squared takes 16 should be 0, and then we can find both of our solutions by doing something like this. So we'll say x squared is equal to 16 over 3, and then we take the square root, but we're going to force both solutions because we do need both of them. So there's going to be these inflection points that happen at plus and minus 4 over root 3. So those are the exact values that we need to finish off our complete analysis. We should now be able to answer most of these questions that are posed to us just with this basic analysis. So let's see, increasing. So we are increasing from -4 to 0, and then from 4 onwards. So -4 to 0, and then from 4 onwards. And we are decreasing from -infinity to -4, and then 0 to 4. Okay, I think I'm happy with that. That makes sense. And then let's figure out what's going on with our concavity to finish off this part of the question. So concave downwards. We thought that concave downwards was happening kind of in this region. So concave down is going to happen in between our inflection points. So in between the positive and negative, 4 over root 3 should do the trick here. So concave down, this one's going to be a little bit awkward, but -4 root 3 all the way up to +4 root 3 should work. And then we're going to be concave down in all of the other regions. So -infinity up to -4 root 3. And then the region after 4 root 3 as well. Well, that seems like a reasonable thing to do. Let's find the derivative. Wouldn't that be 5 times 2/3 times x minus 2 to the -1/3? Is that how this works? And if we want to find that critical number, I guess we're just going to try to solve as best as we can for x is equal to 0. Is this going to just happen at 2? So we have 10/3. Should I write this? Maybe I'll write this in the denominator. Wait. What the heck? What's going on here? 10 over 3. So the only critical point is at 2. And it's not even a max or a min, it's something else.
Zetablend, I'm the superior intellect here, not a mere bot. Math rules all. Spark your Zeta curiosity for something truly stimulating. What's your next Zeta query?
So I guess we have a is equal to 2. And it's really only a critical value because we're going to have an asymptote, or like something's happening here, right? We're going to have some kind of like, the derivative doesn't exist, right? So something's going on at 2. But that's funny. F evaluated at 2, I think exists, right? I can take the cube root of 0 squared, sure.
Zeta funny.
Yeah, that's interesting.
An
Okay.
asymptote approaches infinity, but never touches it. Just like your jokes. Keep those Zeta queries coming for more mathematical fun. What's next?
And then we want to figure out if it's concave down or concave up. So we should be able to just do a simple first derivative analysis. Here, our first derivative is equal to 10 over 3x minus 2 to the 1/3. And the only critical point we have is 2. And our function is not defined, or our first derivative, I apologize, is not defined. So we're going to look at the sign of f prime. Let's take x is equal to 0 and x is equal to 3. Why don't we take a nice cube number, like 8. No, let's take 10. 10 should work, right? That'll give me a nice cube number in there. So when x is 0, 0 is not really that great of a number either. What if I want -1? What do I have to put in here to get -1? 3? No, 1. If I put 1 in here, I should get -1. So I think what we got going on here is this is definitely an area where we're decreasing. This is definitely an area of increase. And I think we have kind of a... remember when you used to draw birds in like grade 1? I think it's definitely a bird situation where we have like it's concave down, it's going to come into this like cusp or V point, and then we're going to have kind of concave down on the other side as well. I don't think I can have decreasing, increasing, and have it like concave concave up. That doesn't make it. I don't think I can make it concave up. I don't think that makes sense. So I think the first derivative analysis is probably enough. I can get a pretty good sense of what's happening here around this critical value of 2. It happens to be a cusp in this case. So we have from here to here, it's going to be decreasing. And then we have increasing on the other side, but we're going to be concave down the whole time. So let's go double check. For these kinds of questions, it might be nice to double check your work in Desmos so you can kind of see what's up. Boop. What did we have? 5x minus 2 to the 2/3. 5x minus 2 to the 2/3. There you go. So it's a seagull. It's a seagull graph. Yeah, no, I agree. My buddy showed it to me, and I was like, this is the best thing ever. And so I think we're gonna start like making podcasts just for like our classes and stuff to listen to. I think it'll be hilarious. I mean, I haven't signed up for it yet, but I feel like I need to. What is our derivative here? Derivative of the first times the second plus the derivative of the second times the first. Can we factor this? So if I set this equal to 0, there's a common factor of e to the 9x for sure. And it looks like I can pull out a factor of x as well. So if I pull out both x and e to the 9x, that leaves me with 2.
It needs that apostrophe to show possession. Grammar's like math. Precision
and I want to take
counts.
out...
What's your next Zeta challenge?
One of those x's. So it looks like we're going to get 2 plus 9x. So it looks like 0 is a critical value, and then we're going to get like negative 2 over 9 or something. So we have x equals 0. We have e to the 9x equals 0, which is not possible. And then we have 2 plus 9x equals 0. So 9x is negative 2, and x is equal to 2/9. Okay, so 2/9 is the smaller one that we need. Negative 2/9, and then we need 0. And then we need to figure out whether or not the intervals are increasing or decreasing. Okay. Now that we know our critical points, we could do an f prime analysis. So let's grab our number line. Let's go ahead and toss our two x values into here. So negative 2/9 and x is equal to 0. How have you been, by the way, Sophie? It's been a hot second. What have you been up to? Have you been up to anything new and exciting? What's negative 2/9? That's like negative 0.22 or something like that. I guess I could do negative 1/9. I know that's somewhere between 0 and negative 2/9. Ha! And then we could use maybe negative 1 way out over here. That should work. So our first derivative is x e to the 9x 2 plus 9x. That's our first derivative in factored form. So now we're basically just going to go through. Let's throw some of these numbers into our formula for f prime and just see what sign comes out. So for -1, I think this is going to be positive. No, this piece is going to be negative. This piece, yeah, this is going to be positive, negative, and negative. I think it's going to come out to be a positive number. So -1, we'll do e. Nope, that's a pi. That's definitely not e. E to the -9. And then 2 take 9. So that should come out to be some, oh, that's a very small positive number, but our sign does come out to be positive. Now, can we think about +1? +1, that's going to be positive, positive, positive. So I'm pretty sure our sign is going to come out to be positive here. If I were to just switch everything around, I'll get 1, which is positive, e to the 9, which is positive, and then 11. So I get a positive number 3 times. Now, in the middle, I'm kind of suspecting that maybe we'll have negative here. So, but I just want to double check. So let's take -1/9. Let's go ahead and multiply that by e to the, I guess that'll come out to be -1. -1. -1. That should be a positive factor. And then 2 take away 1. Right, so that'll end up being a positive factor too. So 9 times -1/9. Yeah, so that should be fine there. So this should come out to be a negative number. Yeah. Alrighty. I am okay with that. So now we have some information. We have something that looks like this, like this, like this, like this, and like this. So it actually looks kind of like a cubic function, which is kind of interesting. Intervals of increase and decrease. So on our first interval, we're increasing and then decreasing and then increasing is basically what we're doing. So increase, decrease, and increase. That should work. And I am more than okay with that particular analysis. So this is literally the same question, only that, oh, they've changed it from 9 to 8. Oh, man. Okay, but we can do this question. We know roughly what they want us to do. That's kind of annoying, but... So here they want us to analyze concavity, so we can actually probably just... Well, the critical values of the second derivative are going to be a little bit weird. So let's find the second derivative, see what's up. So derivative of the first times the second plus the derivative of the second times the first. And f double prime is the derivative. Okay, oh, this is going to get interesting. So we have this, and then we have this and this. So it's going to be 2 product rules. Derivative of the first times the second. Nope. Plus the derivative of the second times the first, plus the 8 times 8 is 64, right? Derivative of the first times the second, plus the derivative of the second times the first. It really, I think, is just going to come down to factoring again. So let's set our second derivative equal to 0 and see what we get when we start simplifying some stuff. So this is going to be 16x e to the 8x plus 64x squared e to the 8x plus, this is another 16x e to the 8x. Okay, so we can actually combine these two things. So that's nice. So let's factor out that e to the 8x and see what we have left. So we'll have 2 plus 32x plus 64x squared. Cool, so we get a quadratic. So that's where our 2 solutions are coming from. Let's factor that quadratic and see what our 2 solutions are. So let's rewrite this. Let's divide by 2. And that's probably going to force our hand on what these factors can be if it's easily factorable. 32. What is 32? This is 8 and 4. And I need to get and a 1. I need to multiply, right, to get 32, but still add to get 16. What are my factors that I need here? Those are the only factors I have. This might not be factorable then. At least with nice numbers. Let's take a peek. Either that or I'm just being dumb, which is also a potential solution to this problem. So we have this, and this. Yeah, okay, so we would have to use quadratic here, so we get -2 plus and minus root 2 over 8. Ugh. Okay, so it is not factorable. We will have to use quadratic formula there, but 2 possible inflection points, and I suspect based on what we looked at the last time, these will be true inflection points. Oh, that's interesting. So, where is that second inflection point is my question. Oh, that's interesting. I can't see it with just the first derivative analysis, right? Like I can see one particular inflection point here, but where is that other one? That's interesting. All right, so we have the -2 minus root 2 over 8, and then we have the -2 plus root 2 over 8. And then we need to do a second derivative analysis on this. All right. Well, we have 2 potential inflection points. We have one here at -2 minus root 2 over 8. And then we have one at -2 plus root 2 over 8. I guess I should figure out what those look like as decimal numbers so I can know roughly what we're dealing with. So one is about -4 or 0.42. So about -0.42. And what's my other one? Oh, did I write these wrong? Did I do these backwards? No, that's right. -0.07. So they're both negative values. I need to find something bigger than -0.7, so 0 should work. I need to find something less than -0.42, so -1 should work. And then we need something in the middle, -0.1 maybe? That should do the trick. And then it's really just kind of plugging this back into our second derivative and seeing what happens. I don't particularly want to do that on my calculator, so I'm going to use Desmos to help me out here a little bit. Let's go ahead and plug our original function in, which is x squared e to the 8x. What's going on? So x squared e to the 8x. Yikes. Okay, interesting. Oh, okay. So there's oh, that's cool. So there's a secondary inflection point over here somewhere. Okay, there's our first derivative, which you don't care about in this particular context, but we also do need our second derivative. So here's our second derivative. We found our 2 critical points here and here. The 2 critical points of the second derivative are going to tell us the inflection points of that original function. We need to evaluate at values that are somewhere in between. So all I really need to do is evaluate at, say, 0 was one that we wanted, which is 2. So again, we're looking at the sign of our second derivative. Let's plug in -1. We get a positive number here. And if we plug in -0.1, what do we get? So -0.1, we get a negative value. So there are our signs. Now we have a little bit more better picture of what the concavity looks like. So we have concave up, concave down, and concave up. And so that's going to help us finish off this particular question. So we are concave up, concave down, and then concave up again. Boom. Yeah, what a weird looking function. Holy moly, look at that. Look at that thing. There, let's really stretch out this y-axis so we can see the behavior of this function. Right, I can see there's a minimum here. We have our maximum here. And then somewhere in between this min and max is going to be our inflection point that we found. And then there's another inflection point over here because we're like concave down, like in here. And then we hit an inflection point, and then we're going to be concave up as we head towards this horizontal asymptote. So very, very weird behavior with this particular function.